do it.
Hi everyone, my name is April.
Hi, I'm Joseph.
This pendulum motion investigation lab was done on August 28th, 2018, along with our partner, Julia.
Yes. So for this lab, we set up an apparatus that is described like this. We had basically a little mounting point for a string, upon which a ball that weighed approximately 36.7 so grams was attached to. We had a protractor here to measure the angle of this along its path. Up here was a photogate to measure every time the pendulum swung through the center line. And with that, we were able to collect the necessary data in both of our procedures.
For procedure 1, we ran 7 trials and we changed the angle of the pendulum every time, and then we observed what effects that had on the period of the pendulum.
Yes, so what we observed by the data here is that at smaller angles, we couldn't even measure, first of all, under 20 degrees because of the way the photogate was set up, but even for smaller angles up to about 30 degrees or so, 20 to 30 degrees, we noticed that the period was rather insignificantly affected by that change at all, and that at larger angles, that the changes started growing and growing much more dependently upon the increase in the angle.
So for procedure 2, instead of changing the angle of the pendulum as we did in procedure 1, we changed the length of the string of the pendulum and ran 10 trials and kept it at 30 degrees.
Yeah, so what we observed here in the correlation between the variable length of the pendulum string and the corresponding time of the period is that so for the most part we did consistent intervals of subtracting 3 centimeters from the length, and we noticed that our period does not get smaller linearly, but for example here, it comes down by 0.04 seconds, then by 0.05 seconds, by 0.05 seconds, by 0.08 seconds, and it keeps taking off more and more time. So we have a nonlinear relationship between the pendulum length and the period of the swing.
You couldn't see your head.
We recreated this graph based off of the data from procedure 1. The graph that we had made in lab had too much information on it because it had each section from each run. So we condensed it and then kind of just based the average of the periods versus the angle, and we put the period on the x-axis and the angles on the y-axis. Interpreting this data, we found that the smaller angles are like from 20 to 30 degrees because it's moving by 0.01. However, from 35 to 40, it's a big jump from 1.48 to 1.51, and then after that, it comes back down to moving only by 0.01.
So we created this graph of length versus the period squared using our data from procedure 2. For the y-axis, we used the length of the string in meters, and for the horizontal axis, or the x-axis, we used the period squared.
Yeah, so upon plotting our data, we got a nice straight line here, the slope of which corresponds with our given equation to be this in the parentheses here, the acceleration of gravity divided by 4 times pi squared. So basically our observed slope of the line is 0.244 meters per second squared because of the units of our graph. We plug that in, set that equal to this quotient here, if you will, and through some algebra, we end up with a product of a unit meters per second squared by a dimensionless unit 4 pi squared as the acceleration of gravity value of being 9.63 meters per second squared overall, which is very close to actual Earth's acceleration of 9.81 meters per second
We then
squared.
found the percent error by taking the absolute value of the theoretical value minus the experimental value and then dividing it by 9.81, which is the theoretical value, and then multiplying it by 100 to get 1.83% error.